is called the steepest descent. Sorry, it's called the conjugate gradient. Okay, conjugate gradient. So, what does conjugate mean? So conjugate means two things or multiple things are tightly coupled together, related to each other. And in optimization, when we say conjugate gradient, there is a definition of conjugate gradient, conjugate direction. So I'm going to give you this definition. Okay, so first we need to give a symmetric matrix, and if we call this matrix Q, so it's some arbitrary matrix, but it's a symmetric matrix, and also two vectors, D1 and D2. So D1 and D2 are important phrase here. Q orthogonal. Or conjugate with respect to Q if what? D1 dot Q dot D2 equals to 0. Okay? So there's a new kind of orthogonal. So what does orthogonal mean? When two vectors are orthogonal, that means they are perpendicular to each other, like perpendicular, 90 degrees. But there's a different way of making these two vectors orthogonal, so-called a conjugate orthogonal. So Q orthogonal. So what does that mean? What does this do? If you remember what we introduced last time, we mentioned a vector dot product, a matrix dot product, another vector is the same as this vector dot product, the result of this. So what is the result of Q dot product D? It's basically another vector, right? So over here, this is a vector. So what does Q do? Q is like a transformation matrix that transform the D2 vector to what? To a new direction, to QD2, right? So Q is like a rotation matrix. It rotates D2, convert D2 to a new direction. And when D1 and this resultant vector dot product equals to 0, that means this D1 is perpendicular to this transformed. So we said this is D1 and D2 is Q orthogonal. So Q represents some kind of transformation. Okay, so this is very important. Okay, and conjugate gradient is using this technique to kind of rotate its gradient direction and try to make sure it has some property between the previous searching direction and the new searching direction, and we will try to make sure the new direction is facing the solution. And I will explain why. I will explain how this can be done. Okay? So, let me see. So there's something that needs to be aware of. So D vectors has to be non-zero vectors. So if your D vectors are zero vectors, it's trivial solution. It doesn't move because D later on is going to be the moving direction. If you have a moving direction with zero, everything zero, you don't move. You don't move. But what happens when you don't move? Your optimization stops. Okay, so this method only works when all the D vectors are not zero. So that which means later on when you try to find a solution, your design can move to somewhere along some D direction. Okay, and okay, I think this is fine. So if you think about this, if I have a initial gas, so-called X0, with the concept of steepest descent, X1 equals to X0 minus alpha gradient F0, right? So if I call negative gradient as, if I name this as my D, let me call this D0 direction. Let me call it D0 direction. Then I can rewrite this as my X0 plus some alpha times a D vector, right? And then based on the same thing, I will have X2 equals to X1 plus some other vector alpha times D1, right? And if I plug in and so on, I have multiple equations like this when I have more and more iterations. But if I plug in, what will happen? What will happen is this X2 is actually X0 plus alpha 0 D0 plus alpha 1 D1, right? So in fact, when we have our solution X star, it's actually a summation of all my solutions. It's like x0 plus alpha 0 d0 plus da da da, and then let's say I converge at some capital K dk. Okay, so it's basically a combination of a lot of directional vectors with some coefficient in the front, and you just keep on move along some direction with some weighting coefficients in front. Okay, so it's always like that. Okay. So if I rewrite this, if I treat this initial gas as origin, so basically my initial gas is a zero vector, right? So we can study what would be the solution based on this origin. So this, when we treat x0 as origin, it's like we move our coordinate system to the initial gas, and the x star is like a new position with respect to that origin. Okay, so this will help us to do the further analysis. So when we do that, this is like how much we move from original design x0, right? Because now x0 is the origin. So when whatever solution we find is like how much we move from the beginning to the end, the total movement, and that's easier for our derivation later on. So when we consider this as the origin, basically it's you can get rid of it because it's a zero vector. Okay, so now let me rewrite certain things so it's actually matching what I would like to do. So let me rewrite as x star equals to alpha 1 d1 plus dot 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 alpha n dn. So let's say I totally have n totally has n vectors and sum together. Okay, so we can rewrite in this form, so it's easier for me to do derivation. So now let's try to do a operation. So what operation? Let's do d1 dot q matrix dot the whole thing. We can do that. We can do any kinds of mathematical operation to this. So what we will get at the end, so this is the what we put in front of the whole equation. So at the end I have d alpha 1 d1 q d1, right, plus da 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 alpha n d1 q dot dn. So every every term has a new dot product operation in front. We do this to every term on both sides of the equation. So what will happen is, assuming D1 to Dn are Q orthogonal. If they are all Q orthogonal, what does that mean? That means every Di dot Q dot Dj, should I say Dj? Yes. So equals to 0. I doesn't equals to j. So every D dot product with Q dot the other D should be 0 if they are Q orthogonal, right? So if we have this assumption, then this equation becomes D1 dot Q dot D1. And how about the remaining? The rest of them become 0 because this is D1 Q D2 until D1 dot Q dot Dn. So the rest of them become 0. All of them are 0. Only this one is not 0. Okay? So we have this new form. And what can we do? We can do this. Alpha 1 then equals to D dot Q dot X star over D1. Oh, this is D1. D1 dot Q dot D1. Okay. So what's interesting is that without doing any optimization, just by playing with the math, we can actually calculate alpha. So what is alpha? Alpha is how much we should move along some di direction. But we don't know how much we should move yet. But over here it tells you, just move this much, and it will satisfy the original solution. This is the solution. It tells you how much you should move. So alpha 1 is how much you should move along the one direction. And if you do the same thing, do same math, but over here you change to D2, then you can calculate alpha 2. So that will help you to find how much you should move along the D2 direction. So it seems like we have something, but it's not yet finished. Why? How come it's not yet finished? Because we don't know X star. If we don't know this, how can we calculate this? This is just at least helping us to derive from some original equation to something we have never seen before. And can we do something with it? And probably we could transform this into something we know instead of something we don't know. So if this is something we know, could that be some way for us to calculate alpha 1? So maybe we don't need to do a very complicated sub-problem. We could actually find the right direction, find how much we move. Okay, so basically that's the idea. Okay. So this is first part of the derivation. To move on to a second part, we need to always go back to what kind of problem we are dealing with. Remember, this is gradient-based optimization, gradient-based minimization. We cannot handle high order functions, like you have a lot of up and down. Because if you have a function like this, too many minimum points. So a gradient approach can only help you to find the bottom of the local minimum. So basically we have some assumption. We can only handle some problem with only one minimum. So usually what does the function look like? It's very similar to a second order function. So remember when we used Newton's method, Newton used a second order Taylor expansion to make an approximation. So similarly, almost every gradient-based method can only handle this nice shaped functions. So the assumption of second order Taylor expansion usually is the way to go. Okay? So the second part of my derivation is here. Based on the second order Taylor expansion, what does f look like? So f will look like this. It will be, let me remind you how the Taylor expansion look like. If some x0 vector is my expansion point, so it should look like this. Okay, this is the second order Taylor expansion. Okay, so in order to make this derivation more friendly to what we want to work on, we need to rewrite this. So how do we rewrite? Let me rewrite this by treating all the constant as a value of c. Hold on. Let me handle, how about this? Okay, what's this? So over here, let's consider Hessian as Q. Okay? So remember we want to do Q of Opt. So now, since we have Taylor expansion, we know we have a matrix over there, which is multiplying the same vector twice. And this form looks like our format of Q of Opt. Okay, so here multiply this and this, we can consider that as our Q. Okay? So we could have this, and we will have a lot of first order terms. So a lot of them. Let me write down which are the first order terms. So basically, if you expand this, this is actually right? If you expand the right hand side, it's like this. And how about if I expand this part? This is like x dot the gradient minus this. Okay, it's like that, right? So this one is actually this one. Okay, the orange one is basically the same term. And how about the other term I want to write down? Over here, let's use minus b vector dot x. So why do I do that? Because we have actually a lot of first order terms, and let me show you which are the first order terms. So this one, and also this one. So Bayesian and x0, they are known information. When you do dot product together, they are just like several a vector with known information. So it's like a coefficient times x. Same here. This is Bayesian is known, x0 is known. This is a known vector multiply unknown x. And here, known gradient, known vector multiply unknown x. So we have a lot of, we have a lot of known vector multiply, known coefficient multiply x. So let's put them all together, rename them as b. No matter what they are, just basically a bunch of known information times b. Okay, so what are the rest? The rest will be the constant part. This is a constant, this will be a constant, and this will be a constant. Because this is just a value, this is known value, dot product, known gradient, known value, dot product, Bayesian, dot product, known vector. So basically all the blue part are just a constant value and sum together. So I would like to write in this way. Let me just say plus c, and everything in blue will combine together into this c value, and everything in purple is merged into this b dot x. So we can rewrite in this form so that it's a nicer way to do the later derivation. And remember, just like Newton's method, what we want is gradient f equals to 0. We want this because we can make sure our solution could be found. So when we say we want gradient f to be 0, what does the above equation look like? What you will have in the end actually is q dot x minus b equals to 0, right? So if we do dot product, do the first order derivative, the gradient of this, because we have two terms here, so it's like the x squared. So we have a power of 2 dropping down to here and multiply with 1/2. We have a coefficient of 1, and the remaining is q dot x. And over here, because we do derivative, so this x disappear, only the coefficient left. So if this is satisfied, this is what you get, and this should be your solution, right? Because when this satisfies, this is your solution. So what we wish is what is gradient equals to 0, and your solution should satisfy this. So x star should satisfy this equation. Okay? So when we do that, we could actually go back and look at what we had earlier. We use some way to derive how to get alpha 1, right? Let's recall this. And did you find something interesting? Compare this and this. Someone's smiling. Very good. I like students smiling. Okay, so I always like to see how people derive optimization because it's always like magic. So look at this part. Q dot x star can be seen here. And this basically equals to B. That means we can replace this by B. So previously we said we couldn't calculate this because we don't know x star. But now we know it's B, then when we replace it, B is something we know. Then it's like playing magic, right? Here I should be missing, here's the 1. Here's the 1. Okay? And what is Q? Q is Bayesian. Q is Bayesian at the top. Okay? So Q is Bayesian because right here, consider this as Q. That's why we could have this, right? So let's check this again. D1 is some direction you decide to go. Bayesian is a second order derivative matrix on that spot. B is a bunch of coefficients. B is what? B is this guy, and this guy. So still, you need a lot of calculation of Bayesian. But at least, you probably don't need to do the alpha search anymore because this way it already tells you what is the alpha. But you are actually still working on Bayesian calculation. So maybe what we have so far is basically the same as Newton's method, just different mathematical form. So can we improve it? Can we get rid of Bayesian so we don't actually need to do Bayesian? So that would be the next step. Can we replace Bayesian? Okay. So let's see. How do we get rid of that? This requires a bunch of derivations. Let me check how can we have let me see if I can make this derivation nicer. dk is blah, blah, blah. Okay, so I think we need to, at least we know this right now, and we need to try to implement this step by step instead of handling so many D vectors and see what we can do. Okay, so now start to do some trial formulations based on what we know so far. Okay, so when we start optimization, we usually don't know what's the proper direction to move. So the only way is that we can only move along the steepest descent direction, the negative gradient direction. That's usually the first step. And the idea is that when you move on to the second iteration, since previously we already know first moving direction, can we consider our second moving direction as a direction which is Q orthogonal to the first one? Then probably we could move faster. So that's the idea. Because we always need, whenever we use this Q orthogonal or conjugate direction, we always need two vectors, two directions. So you always need an initial one. Then you use it to calculate the next one. So the initial one has no reference. So the initial one usually is exactly the same as steepest descent. Okay, first, use steepest descent to determine di, basically d1, the first moving direction. Okay, let me make sure if I would like to use d1, because the numbering sometimes is confusing. D1. Usually we start with k equals to 0, right? But I never use D0. I hope it doesn't confuse you. Okay, to deter. Let's use the, let me see my notes. Do I start from k equals to 0 or k equals to 1? Actually, it doesn't matter, but I don't want to confuse you with the previous treatment. Okay, let's use D0. Okay. So it's like k starts from 0. Okay, I'm sorry that when I derive over here, I didn't choose D0. Actually, I did over here, D0, but over here when I write, I start from 1. It doesn't matter. It doesn't matter. It's just an index. There are basically many of them. Okay, so now if we use steepest descent, we chose some moving direction, and of course, based on steepest descent, D0 is negative gradient, and plug in my initial guess. Okay. Or to be, let me write it down like this. To be having a shorter, cleaner derivation, because there's going to be long derivations later on. Okay, so based on steepest descent, x1 equals to x0 minus alpha 0 times gradient f0, right? So based on that, based on my new mathematical definition, I can rewrite as plus alpha 0 d0, because d0 basically is negative gradient 0. Okay, so I can rewrite in this way, and of course, this equation always works if I add on my index k. So actually, xk plus 1 equals to xk plus some alpha k times dk. Right? Okay? But how do we determine dk when we move on to a next direction or next iteration? So initially I said we can use dp's decent, but in the second or later iterations, how do we determine dk? We wish this is having q orthogonal with the previous d, right? So here we need to make one definition. So we have some numbering of the equations. So over here, dk. We define dk as the following form. Is negative gradient evaluated at kth point plus some beta value, and here we use k minus 1 times d vector k minus 1. So what is that? So we at kth iteration we still move along the negative gradient direction, but we would like to do some updates. So we use a summation with the previous direction multiply some. Actually, this should be a dot product. Beta should be a beta. Beta is a value, or let me see. Beta is a value. Yes. Beta. Yes, beta is a value. So we want to plus some coefficient times the previous d. We just define my new moving direction looks like this. And then if we define this equation in this form, can we make sure this is having q orthogonal with the previous d? So with that request or that wish, see if we can derive what does beta look like. Okay? So that is a very important equation because we will need to calculate beta later on. Okay? So if we do this, so far we have some unknowns. We don't know alpha k. We don't know beta k minus 1. So far, alpha k and beta k minus 1 are still unknown. So we need to figure out a way to determine these two. Okay? And we wish what? We wish